Hi, I am Parth Deshpande from the Center for Sustainable Road Freight at the University of Cambridge, and I shall be presenting our work on accelerating road freight electrification using electric road systems in different countries. Starting off with some road freight statistics, we see that there has been a rapid growth in road freight in countries like India and China in the past few years. The absolute freight volumes in India, China, and the US are also much higher than in countries like the UK and Europe combined. Hence, there is a need to focus on evaluating electrification solutions like the ERS for these countries. There are many possible implementations of electric road systems or ERS. Here we focus on this particular implementation where there are overhead catenary cables that charge a battery electric truck using a pantograph. This type of implementation is the most efficient and is best suited for heavy goods vehicles or HGVs. Hence, this work focuses on the overhead catenary implementation of the ERS. It is divided into two parts, where we first look at the feasibility of the ERS in terms of the cost break-even of the infrastructure and the effectiveness in terms of the battery sizes needed to complete specific journeys on and off the ERS. Starting off with the cost break-even model, the aim here is to find how many trucks per day would be required to use the ERS in order for it to pay for itself, or in other words, to achieve cost break-even within a certain duration. This is done by factoring in the costs involved in constructing 1 kilometer of the ERS, where the expenditure is the cost of the infrastructure on loan and an annual maintenance cost, and the income is generated by selling electricity to the trucks. This of course depends on the number of trucks using the ERS. This number of trucks is obtained using the equation on the right, which is defined in terms of the capital cost of the ERS, the break-even duration, the loan installment, the maintenance costs, the duration of the construction period, inflation, the ramp-up curve, and the duration of the ramp-up, the usage of the ERS per year, the energy transferred to one vehicle, and the electricity profit margin, which could be a variable. The plot here shows a graphical representation of some of these parameters, where on the x-axis we have the electricity profit margin, and on the y-axis we have the number of trucks per day. The different curves correspond to the different break-even durations. What we notice here is that they taper off after a certain value for the electricity profit margin, and hence it is best to keep the profit margin below 12p per kilowatt hour. Now, in cases where we do not have the data for the number of trucks, the same calculation could also be done in terms of the annual freight flow on a certain section of road. Now, this is represented in terms of the energy transfer to the vehicle, the number of trucks on the road, the usage per year, and the average energy efficiency of road freight in that country. Now, the plot on this slide shows the variation in these costs with respect to time, where the blue curve represents the expenditure and the red dashed curve represents the income. There is no income for the first 5 years, which account for the construction time. This is followed by the time required to ramp up the usage. The loan ends at 30 years here, which is why the expenditure drops after this time. And the point where these curves cross is the break-even point, which in this case is less than 20 years for a peak usage of 3,000 trucks per day. Based on this analysis, the roads in a country can be highlighted to denote the break-even duration if an ERS section were to be constructed there. This is done for 4 cases as seen in the table here with varying parameters, where A is the base case, B represents an increased profit margin, C is lower infrastructure costs, and D is a longer loan duration. Now, as seen here, the ERS is economically feasible over most of the strategic road network in England, which is shown in green. This also includes the M180 motorway, which is the site for a proposed ERS demonstrator by the UK government. Also seen here is that cases A and D give us very similar results, as do B and C, and hence only cases A and B are analyzed for the other countries in the next slide. This analysis can now be extended to more countries that have available data on freight flow. Starting with India, it is seen that in the base scenario, the highway from Delhi to Kolkata, which is a part of the Asian Highway 1, shows us the best economic feasibility for the ERS. Increasing the profit margin in case B extends this to more highways that are part of the Golden Quadrilateral between Mumbai, Delhi, Kolkata, and Chennai. This also includes the Delhi-Mumbai section, which the Indian government recently announced their interest in building an ERS section on. Moving on to South Africa, both cases include the two major freight routes in the country that are the N1 and N3 that connect Johannesburg to Cape Town and Durban respectively. This does not change much in the second scenario as the road freight in South Africa is mostly concentrated on these two highways. Meanwhile, in France, we see an interesting case because the most popular routes are the ones connecting other European countries, for example, Spain and Germany, while passing through the two major French cities of Paris and Lyon. Do note that the infrastructure costs in India and South Africa here are assumed to be slightly lower because of the lower labor costs in these countries. In terms of the amount of electrification possible using these scenarios, we see that in England, the lane kilometers electrified are very high because of the road freight being spread across evenly on the SRN, or the strategic road network. Meanwhile, in France, the freight is concentrated on the international freight routes that we spoke about, thus leading to a larger amount of electrification despite a smaller proportion of road length being electrified. In India, the road freight is dense on major routes but is geographically sparse otherwise, which results in lower numbers overall for freight electrification. But then, when we increase the profit margin, it significantly increases the amount of electrification because the market is very price sensitive. In South Africa, on the other hand, we see that there is another extreme where all the road freight is concentrated on the two major freight routes, which is why we have higher freight electrification with smaller road lengths being electrified. Moving on to the next section of this work, which is about analyzing specific journeys. So based on these feasible locations of the ERS and the origins and destinations of the journey, we can use the SRF drive cycle generator to create a velocity profile for a vehicle on that journey. And this velocity profile is followed by a driver and vehicle model, which gives us the energy consumption of the vehicle as well as the battery size required to complete that specific journey. More information on this can be found in the paper at the bottom of the slide. Now this methodology can be used to analyze the effectiveness of the ERS on some journeys. One example of a journey is shown here for a logistics company in South Africa. The journey starts at the green pointer in Durban and goes up to the red one in Pretoria. It is a single day journey and there are two rest stops and one drop stop along the way, all of which are shown in blue. Now the table below shows us the different battery sizes required for this journey with different charging scenarios. When there is no ERS or static charging, the battery size required is a massive 1700 kilowatt hours, which is definitely not a feasible size for a truck. But then introducing the ERS as per case A, which is now shown on the map in light blue, with drop stop charging reduces the battery size required to just around 150 kilowatt hours. When we add in more of the ERS as per case B, it reduces further to less than 100 kilowatt hours as we no longer need to stop for static charging because the static charges are along the ERS and thus the need for charging is eliminated. Now the other type of journey that can be analyzed here is a multi-day tramping journey with overnight stops. And in this case, we can see that on days 3 and 4, a major part of the journey is outside the ERS, and we shall see the effect of that on the next slide. So on this slide, the table here shows us the battery sizes required for all 4 days for this journey. And while the journeys on the first 2 days are entirely on the ERS, the largest battery size requirement is on day 4, which is almost 800 kilowatt hours even with ERS case B. And for such a journey, what we see is that it is essential that the ERS should be complemented by either more charging stops or a hybrid range extender that would run on biofuels. But then if we look at the overall results here, it makes sure that the ERS does most of the heavy lifting by covering a majority of the freight journeys, and the other solutions that are static charging or range extenders can be reserved for the specific use cases where, for example, we have to go off the ERS. With that said, we saw in this presentation that the ERS can electrify these major freight routes while being able to pay for itself. Now there were some differences in the countries studied because of the geographical distribution of road freight or the economics in that market. But this also meant that the final decarbonization solutions there would be a mix of the ERS and other technologies. Having said that, this study could act as a base for governments to form the right policies for road freight decarbonization in the countries. And some next steps could be evaluating the other technologies mentioned, including static charges and range extenders for these journeys, and also studying more journeys from other fleet operators in more countries as well. Thank you very much for listening to this presentation.